The reason we're doing it is to see a nice application again of really the fundamental theorem of arithmetic. It's really everything, many things we do in number theory just are talking all the time about the prime factorization of integers and the fact that integers can be represented as products of primes. And also some analysis or calculus ideas from first year. So obviously everything we covered in first year is fresh in your minds. Yes?
What's the FTA?
FTA, Fundamental Theorem of Arithmetic.
Oh, I thought that's a H.
No, FTA, yeah. Fundamental Theorem of Arithmetic. Yeah. So everything from the first year is fresh in your minds, of course. Okay. So one of the nicest things we saw in first year was we saw the harmonic series. Okay. Everyone remember what the harmonic series was? The harmonic series. Now it's an alternating series. You're thinking of plus minus, plus minus. Harmonic series was called the harmonic series because it refers to the locations of some of the harmonic points on a vibrating string. If you play a stringed instrument, you know if you deaden the string in the middle, it'll still vibrate and sound a note because the two halves are then free to oscillate, and that's one of its modes of vibration of the string, the two halves oscillating independently. Also, if you deaden it at a position that's a third way along the length, or any multiple of that, it'll still sound a note, be less loud, less powerful, but the note is still there because the different thirds of the string will be oscillating independently. And these modes of vibration are basically located at every fraction like that. Okay? So the so-called harmonic series is the series adding up all these values. Now, what was it we proved about this series in some of our initial lectures on the topic? What was the key thing about this series that was significant? Yeah.
It does not converge.
It does not converge. Yeah. Which is divergent. Yeah. It does not converge. Okay. And this was very interesting for us. The terms are converging to zero. The terms are vanishing, so to speak. Okay. Each term is getting smaller and smaller, and they're dwindling away, getting arbitrarily small. But yet, when you add them all up, you still can achieve. If you wait around long enough, you will see that sum grow to any size that you care to specify. You'll have to wait a very long time. Any upper limit, any large number that you specify, if you wait around long enough, you'll eventually see this sum go past that value. Okay? So it's divergent. It's growing without any upper bound. If you remember the proof of it, we see if you gather these two together, this is larger than a half because it's bigger than 2/4. And if you group a fifth, a sixth, a seventh, and an eighth together, see all those fractions are bigger than or equal to an eighth. So that group is bigger than 4/8, so that's bigger than a half. So you keep grouping together, you double the number of elements in each group at each point, and each group is bigger than a half. So that's how the sum is growing. So you're constantly generating extra halves, and so that will get you to any value that you want to get to. So that was good. Another series we saw was, say, the sum of 1 over n squared. The key thing about this is, in contrast to the harmonic series, this series did converge. 16, etc. Okay. So this was convergent. Again, the terms are dwindling away, they're converging away towards nothing. And yet, this sum will not grow and grow without any upper bound. It just sums to a finite value. I should know the value off the top of my head, but does anybody know? It's approximately, it's low. It's probably less than 10. So it's small. We can prove that formally using the integral test. Do you remember the integral test? Because the series compares to the integral of 1 over n squared. Say from 1 to infinity. So it's 1 over t squared dt. The fact that integral converges to a finite value, then that tells you the sum has to converge as well. But those were two key series, two key things about them. But of course, sum of 1 over n squared is a subseries of sum of 1 over n. Yeah, because within sum of 1 over n, you've got plus 1 over 9. Sum of 1 over n squared is just sum of the terms from the series sum of 1 over n. That makes sense, yeah? Here you're taking the denominator is every integer. Here the denominator is just the square of integers. So you can have a divergent series, but within it, if you just pick out certain terms, leave out most of the terms, and just admit some of the terms, then you can have a convergent series. Okay? And the reason the harmonic series diverges is because its terms do not converge to zero fast enough. They do converge to zero, but they don't do so fast enough. So there's still enough weight, there's still enough accumulation in them to make this sum grow and grow and grow. Whereas the sum of 1 over n squared, these do converge to zero, and they converge to zero fast enough so that even though each of them is a positive thing, and even though this sum is growing all the time, but it's growing by ever smaller and smaller amounts, as is the harmonic series, of course, but it's doing so slow enough that it will converge, the infinite series that converges. So this lecture is about, or what we're going to discuss, is about another interesting subseries of that. So number theory is all about the primes, right? So what we're going to talk about is what about the status of the sum of 1 over p, okay? Where you sum over all p. When you see p in number theory, it means a prime number, okay? So summing over all the primes, okay? So the sum of over p, of 1 over p, this is, so the first prime is a half, second prime is a third, next prime is a fifth, seventh, then 9, 10, 11, 13, etc. See it up here, it's just a subseries, a half, a third, a fifth, a seventh. Okay. So we're leaving out some of the terms of the harmonic series and letting other ones. Okay. Now most integers are not prime, of course. Most integers are not prime. If you look at any interval of integers, most of the numbers will not be prime. So the primes are only some of the numbers. By just looking at how frequently the squares appear and how frequently the primes appear, you'll notice, and it is true, primes appear more frequently than squares. Okay, by the 1, 2, 3, by the fourth square, you're already up to 16. By the fourth prime, you're still only at 7. So these squares squares, the gaps between the squares get longer and longer, bigger than the gaps between the primes, just from observation. So the behavior of the sum of 1 over p will be somewhere between that of the harmonic series and the sum of 1 over n squared. So somewhere between diverging and converging. So that means its status is uncertain. Does it converge or does it diverge? So the behavior of this is between that of the sum of 1 over n and the sum of 1 over n squared. So does it converge? Okay. So we're going to prove whether it does or not. Anybody know? Anybody know the answer? Have you encountered this before? Cool. Excellent. Good. Okay, so it's uncertain. Does it converge to a number or not? And remember, it's remarkable that we can answer this question because we don't know what all the primes are. Yeah, we've only been able, using computers, to accumulate a certain number of prime numbers up to now to discover them. Even though we've discovered very, very, very large primes, those Mersenne, there are records for discovering the largest known prime number. But these largest known prime numbers, there's huge gaps. There's loads of primes, before then that we haven't obtained at all. Okay, so we've got a certain continuous knowledge of the primes from the beginning up to some upper point. Interesting to know what the largest prime in that consecutive series of primes is that we know. It'd be an awful lot lower than the largest prime that we know. And then we know some sporadic primes that are very, very far out. There's loads of primes in the middle we don't know. And then there's all the primes beyond that. Of course, there's an infinite number of primes, but we don't know what they are. Of course, there are algorithms that can find them. And our computers have found a certain number. But it's interesting that we here, using our first and second year maths, can still answer this question about whether or not this sum converges with it. Okay? So that's interesting. Just the fact that we're able to get at the answer to that question. Okay. And we're going to be able to do it with reference to the known behavior of the harmonic series and the sum of the 1 over n squared series. And in the course of doing it, we're going to see some interesting manipulations as well. I just have to remind myself how some of this goes. Okay, so our first task, we're going to start from our knowledge of, we're basing it all on our knowledge of the harmonic series. So the first task is to use the FTA to rewrite the sum of 1 over n in terms of primes. And, well, I'm just going to put it down on the page. Now, you won't believe me at first, but if we take the product over all primes of, the sum of the powers of 1 over p. We're going to look at this. This thing. What is this thing? This thing is a product over all the prime numbers of each of these brackets. Okay? In any one bracket, you've got all the powers of 1 over p for that prime. Okay? So the first of these brackets is the bracket for the prime 2. So it's 1 plus a half plus a quarter plus an eighth, etc. The next bracket is the bracket for, so let's write that down, 1 plus a half plus a quarter plus an eighth, etc. The next bracket is the bracket for third, for the prime 3, 1 over 9, 1 over 81, no, 1 over 27, 1 over 81. multiplied by the next bracket is the bracket for 5. 25, 1 over 75, etc., etc. Next one is the bracket for 7th. You get the idea.
Yeah.
Probably. Yeah. 125, yeah. Details. Okay. So it's a product of all those brackets. Each bracket is an infinite sum. Okay. And there's some number of brackets. There's one bracket for each prime. I'm going to argue this without any explicit reference yet to whether or not there's an infinite number of primes or not. An interesting thing to note is our proof of the FTA did not rely on us already knowing that there were an infinite number of primes or not. Okay, so the FTA is silent. If you look at the chain of reasoning that went to the proof of the fundamental theorem, it was silent on whether or not there's an infinite number of primes or not. It didn't need that knowledge. So our proof of the FTA is, you could say, agnostic on the amount of primes, on the infinitude or not of primes. So that's just an interesting remark. So I'm just going to be a bit vague about how many of these brackets there are. But we have one for every prime number. And we know the fundamental theorem of arithmetic is true, that every number can be written as a product of primes. Now, what could this product be used? Well, let's think about it. Think about, in principle, how you multiply the brackets together. Right? You've got one big bracket of a sum of loads of terms, and a second big bracket with a sum of loads of terms. How do you multiply the two together? Well, you have to take all possible products. So something from the first bracket multiplied by something from the second bracket. Those are your individual products. And you add up all possible products. Yeah? Does that make sense? And if you've got 3 brackets that you want to multiply together, and each bracket is a sum of terms, right? How do you multiply those together? Well, the result is going to be a big sum of terms. Each term in the big sum is going to be a product of one thing from the first bracket, one thing from the second bracket, and one thing from the third bracket. And you have all possible combinations. Something from the first time, something from the second time, something from the third. Okay? So that's the principle we keep in mind. We multiply brackets together, and the brackets are big sums. You multiply them together, it turns into a big sum of terms. Each term that goes down here is made up as a product of something from here, times something from here, times something from here, times something from here, over however many brackets there are. So what possible terms can you get? Well, you get terms that are 1 over something. And the denominator is made as a product of, one denominator from here, one denominator from here, one denominator from here, one denominator from here. Now the denominators here are powers of 2. The denominators here are powers of 3. Denominators here are powers of 5, powers of 7, etc. And included in each bracket is the 0th power. So the denominators here are basically anything that can be written as a product of powers of primes. But what does that sound like? Yeah, and any integer. That's the point from the fundamental theorem of arithmetic. Okay. The possible things that are written as products of powers of primes, and I can take some power of 2, including the 0th power, really no 2's if I want, some power of 3, some power of 5, some power of 7, choosing one power from each prime number, build that up as a product. Well, if I've got complete freedom here, as I have, I can build up any integer, any positive integer. So basically, we're saying that that's the sum over every possible n, the sum of n over n, including our harmonic series. So which is the harmonic series? The harmonic series. We didn't recognize it at the beginning because it's written in an extremely strange way. This is a really simple expression of the harmonic series. This is extremely convoluted. Now you may object to this notion of products, especially if you remember, but there's an infinite number of prime numbers. Well, if there's an infinite number of prime numbers, that means you've got an infinite number of these brackets, and surely that messes the thing up, or surely that makes it complicated, or... Well, it does kind of, but... So even if we allow, which we have to, we allow for the fact that there could be an infinite number of products, infinite number of brackets, you don't run into any problems, because the only terms that actually make it down to this line, the only terms that survive are the ones where all but a finite number of choices are the number 1 from each bracket. Because if you make a choice of a power of 1 over p from each bracket, if you say, let's say you chose the first 1 over p from each bracket, so you're multiplying a half by a third, by a fifth, by a seventh, and you continue choosing that 1 over p from every bracket, what would you end up with at the end when you multiply them all together? Yeah, basically 0. That sounds like you're sitting on the fence. Yeah, and there's an infinite number of prime numbers, and you're always choosing 1 over p. If you keep multiplying, if you multiply a half by a third, by a fifth, by a seventh, by an 11th. Sorry? 1 over 13. I mean, you're there. I'm just trying to push you over the edge. It is 0. It is 0. If you multiply together 1 over p for every p, you're multiplying together a series of fractions that are getting smaller and smaller and smaller. They're all less than 1. What happens when you multiply something by less than 1? It gets smaller still. And if you multiply by something very much less than 1, very close to 0, it gets even smaller. And you're doing that an infinite number of times, it's converging to 0. So if you choose some of these non-trivial terms from an infinite number of brackets, it's not going to survive down to this line, so it's going to dwindle away to nothing. So it doesn't need to be included here. So the only things that do survive are ones where all but a finite number of your choices are the number 1 from each bracket. So you can choose some funny numbers from a finite number of brackets, but then all the others, the infinite remaining choices, must be 1. That's the only way that your choice can produce a term that's going to survive to this. And the kind of things you choose, products of a certain number of primes, powers of those primes, it's some kind of integer you're choosing. And you're never choosing an integer, so say the third, 1 over whatever, it can only be formed in one way, because the fundamental theorem of arithmetic said prime factorizations are unique. So each reciprocal, 1 over whatever, is associated to a unique choice of term from each of these big brackets. So that is all about the justification for this equal sign. Okay. This is the harmonic series. So that's the main step at the start to establish that. And then we're going to, okay. So sum of 1 over n is equal to the product of 1 over p by the sum of 1 over p to the j greater than or equal to 0. Sorry about that scribble in the note. Okay. So it's the product over all p of these sums. Okay, that's what each of our brackets looks like. The sum of the powers of 1 over p for every j greater than 0. Now we know what this is. What is that? First year stuff. It's a certain kind of series. It's a series that we've got complete knowledge of. Type of series we've got complete knowledge of. a series of terms. Each term is a multiple of the previous one, fixed multiple. Because it goes 1 over p, then the next term is 1 over p squared. So multiplying by 1 over p all the time. Next term is 1 over p cubed. Geometric series. Yes. So this is a geometric series. The sum of AR to the n minus 1, where A is equal to 1 and your R is your 1 over P. I should have put J minus 1. So the first term is 1 and the common ratio is, sorry, first year we always start to the sum at 1. Here it starts at 0, but it all works out. So it's a geometric series with first term 1, common ratio 1 over P. So that means it has a nice value. It's 1 over 1 minus 1 over P. Remember the formula was A over 1 minus R. If it converges. And it converges if the common ratio is less than 1. So it definitely convergent. So we got this nice expression. This looks strange, but nice. So the sum of the harmonic series is the product over all primes of this. Okay? And we're still agnostic. We're still avoiding the question of is there an infinite number of primes or not. But this is where it goes a bit strange. We're going to take the logarithm of both sides. Now, you could make an objection here. In court, you could shed objection, Your Honour. We started out saying the harmonic series is divergent, right? So technically, formally, I shouldn't be taking the logarithm of it because I'm trying to take the logarithm of infinity. So we're into the realms of loose mathematics, in a way. Formally, it's not correct, as I've stated here, because what do I mean by the logarithm of infinity? So we're into a bit loose, a bit vague, a bit dangerously close to the edge, loose talk, so to speak. But it's still valid. It's still valid, okay? The underlying idea is you can make this kind of talk rigorous if you express it carefully in terms of partial sums and convergence and so on. Or even set it up symbolically that, we're just talking about applying the logarithm to a summation process and applying the logarithm to a product process. Okay. But we'll go with it for now because it'll get us what we want. And lots of people do mathematics in a slightly, especially physicists in advanced physics, quantum physics and all that, they play around very loosely with infinities and that sometimes. As long as you do it very carefully, as long as you respect some underlying principles, it still makes sense. So we're going to go for it for now. And we're going to use what we know about logarithms. So first thing, what happens when you take the logarithm of a product?
Breaks it down to small log.
One log, yeah. So it's the log of a product is the sum of the logs. Yeah, exactly right. One log plus another. So the logarithm of this product is the sum of the individual logs of 1 over 1 minus 1 over p. Summing over p. Another property of log.
I think it's like 1 over, no, it's the numerator. The log of the numerator take the log of the denominator.
Yeah, and the logarithm of this numerator is the logarithm. Yeah, so the logarithm of a quotient is the difference of the logarithms. Yeah. The logarithm of the top minus logarithm of the bottom. The logarithm of the top is 0. Logarithm of 1 is 0. So we don't have the logarithm of the top. We just have the sum of 1 over p minus the logarithm of 1 minus 1 over p. Simplify it yet again. So that first of all, that minus sign can come out. And now we're going to use the Taylor series for the logarithm. But the logarithm function expanded about 1. And the logarithm function expanded about 1, let me look it up, was 1 minus x. So it's minus x minus a half minus a third. So if this is, 1 minus x, this becomes minus x minus a half x squared. Yeah, so it's the infinite sum of minus 1 over n x to the n of 1. Okay, so that's the Taylor. So again, this is first year stuff. So it's the Taylor series for the logarithm function expanded about 1, with 1 as the base point. And this is probably, it might only be valid for, it's probably only valid for x with an absolute value less than 1. But that is the case here because we're dealing with 1 over prime. So we apply this. But then see these have minus signs all over them. So we've got an extra minus sign out here. So we'll turn it all into positives. So it's sum 1 over p plus 1 over 2p squared plus 1 over 3p cubed plus 1 over 4p4, etc. And this was our goal here because now we can finally see our prime harmonic series. Here it is here at the beginning. The sum of 1 over p. That's what we want to describe. The sum of 1 over p. So we separate it off. Okay. That's our prime harmonic series, it's sometimes called. And we've got all the rest. All of the other terms. Now, all the other terms we can do something with. We can simplify them a little bit. You see, if I leave out the 1 over p, then everything that comes afterwards has a factor of p squared in the denominator, so I could factorize that out. So I'd be left with a half plus a third times 1 over p plus a quarter times 1 over p squared, etc., etc. Yeah. Yeah. Now this is what we're interested in. We want to keep this as long as we have. Remember, what's the left-hand side of this equation? The left-hand side of this equation is the logarithm of the harmonic series. Now we got our prime harmonic series here, which is nice, and we got all this stuff. So we want to work. We need to understand all this. The first way we're going to understand it is, well, these factors here are big. The factors of a half and a third and a quarter and so on are a little bit confusing, but I can throw them all away with the understanding that I'm making this bigger. Okay, so just throw away all those factors of a half and a third and a quarter. Don't really need them. Because suddenly there you see our old friend, the geometric series again. Yeah. That geometric series again. There it is again, and we know what that is. That's got a formula. It's 1 over 1 minus 1 over p. Okay, which has reduced that infinite bracket there. to just this fixed quantity, and now we just have to multiply it by 1 over p squared, and it's going to be 1 over p squared minus p. Now, what can we say? Remember, we ultimately we want to say something about this, the prime harmonic series. On the left-hand side, we've got the logarithm of the harmonic series, which is the kind of the logarithm of infinity, kind of. But what can we say about the sum? So it's a series 1 over p squared minus p. Well, the problem is, okay, if there's a finite number of primes, this is just some finite number. But we know there's an infinite number of primes, so this is an infinite series. So we have to wonder about whether it converges or diverges. Okay. But you see, we know that the sum of 1 over n squared converges. So by comparison with that, remember we did comparison tests last year, not fundamentals. If you've got a series that you know converges, well then if you encounter a series which is smaller than your convergent one, or that the terms are smaller than your convergent one, then you know that this new series has to converge as well. Okay? Because for infinite series of positive terms, convergence is a good behavior, which means the terms are getting small very fast. So if we find a new series which we observe the terms getting smaller and faster than the well-behaved ones, it means that this new series is even better behaved. So it too converges. So 1 over p squared minus p, okay, it's essentially 1 over p squared. That's going to be the dominant part as the prime gets large. But you know the primes are infrequent. Here we're summing over every n squared. Summing over 1 over p squared means you only encounter some of the terms from this series. Okay? So this series behaves better than this. It's less than this. By comparison, it's smaller than this, so therefore it must converge. Okay? By comparison, so that's a technical matter using one of the comparison tests, either the standard comparison test or the limit comparison test. The comparison test can show that the sum of over p, 1 over p squared minus p, also converges. So if it also converges, it means it's just equal to some number. That's okay. Converges. The sequence of partial sums converges to some fixed quantity. So what we've got the logarithm of the harmonic series, and along the way we lost our equality along the way, but it's strictly less than our prime harmonic series plus some number. Some positive number, okay, which is the sum of that series. Okay, and any questions about I mean, I still haven't finished off the conclusion. But so what does this say? What does this say about sum of 1 over p? If the sum of 1 over p was convergent, right, that means this sum would just have some fixed value, okay, whatever the limit of the sum is. Okay. So what we'd be saying is that the logarithm of the harmonic series is bounded above. Okay. But you can't say that because we already know the harmonic series is divergent. It's equal to infinity, so to speak. Okay? It's an unbounded infinite sum. So its logarithm can't be bounded above. Okay? the logarithm of this was strictly less than some fixed finite number, that would mean that this was a convergent series. Okay? So you just take the exponential of that, and you've got an upper bound for the series. Therefore, the series can't diverge. But we already know it does converge. If it's convergent, we get a contradiction, i.e. the logarithm of the harmonic series is bounded above. That's the contradiction. It can't be bounded above because the harmonic series is divergent. Okay? Sum of 1 over n is divergent. So the conclusion is, therefore, sum of p, 1 over p, is divergent. Okay? We've been able to prove that, even though we don't know what all the prime numbers are. Nobody knows what all the prime numbers are. We have algorithms that will definitely list them all, but they can't really be executed in a, they get bogged down, they get slower and slower. So therefore, this series is divergent. And also, our analysis there, okay, I referred to it a few times, but the analysis there goes through whether or not the prime numbers are infinite or not to an extent. Okay? So this gives us a second proof that there's an infinite number of prime numbers. So we would have been able to do all this analysis if, hypothetically, there were only a finite number of prime numbers. But of course, if there's only a finite number of prime numbers, that sum has to converge. If there's only a finite number of prime numbers, this would just be a sum, some finite bunch of fractions added together. It's going to have some fixed value. Okay, there's no convergence or divergence question if it's a finite sum. So therefore, there can't be only a finite number of prime numbers, because we've just proved that this is divergent. So there must be an infinite number of prime numbers. Also proves there are infinitely many prime numbers. As otherwise, sum over p, 1 over p, would just be 1 over p1 plus 1 over pn, however many primes there are. So that would be a convergent series. But we've just proved it's not, so it can't be a convergent. So I hope you like that. It's a important result, interesting result, and it shows a nice interaction of some first-year ideas from the convergence of infinite series, Taylor series, things like that. But crucially, all the way through it, to get us started with this funny version of the harmonic series, as this infinite product, we needed essentially the fundamental theorem of arithmetic playing an essential role as well. Now, this argument, as I say, it's a little bit iffy, or a little bit, you can maybe object to some of the details, because we started off with taking the logarithm of a divergent series, which strictly speaking you shouldn't do. But you can also prove this much more formally as well. I had hoped to fit that in as well, but I didn't want to rush through it. So we can also prove divergence completely formally, completely rigorously, using first plus second year concepts. I'll maybe show you that to you next term. Okay. So we'll end there for this morning.